Hello and welcome to our lesson on rates of change. So a rate of change for a function is describing the rate at which specifically the outputs are changing with respect to the inputs. And that sounds like a lot of fanciness, but I'm sure you've dealt with rate of change before. Rate of change is just slope, okay? So when we're describing the rate at which outputs change with respect to the inputs, we're talking about a rise over run or a change in y values. That's what our outputs are generally with respect to the change in the inputs, those x values. So it's just slope. Okay, the rate of change for a function is slope. And again, I know we've seen slope before. So slope, we use the letter m to signify. I theorize that m is used because it's describing the movement from one point to the next, but again, we could call that slope our rise over our run, where our rise is our change in y values and our run is our change in x values, and that's what that little delta stands for. And the change in our y values we could always find by subtracting those two y values, and the change in our x values we could always find by subtracting those two x values. Okay, so slope, not a new concept. However, when we talk about slope, generally we think about linear functions. So for example, this blue line I have here, wherever we are on this line, our slope is going to be constant. The rate of change between 2 points doesn't change. So if we had a slope of, let's say, 2, I could rise 2, run 1 to get to the next point, and that's going to be true from any point to the next along the graph of a linear function. But if we're dealing with a function that is not linear, suppose it's this red one here, then the slope will vary from one point to the next. For example, I have a negative slope here, I have a positive slope here, because the graph is decreasing and then it turns, then it's increasing. And some of the places on this graph have steeper slopes, like this is going to be much steeper than, let's say, the slope here. So both of those are positive, but they're definitely different. So if I want to find the slope or the rate of change between points on a non-linear function, I have to give myself some frame of reference. So I have to say, okay, what part of this function am I looking at? So let's say I wanted to find the slope over this interval of this red curve here. If I want to find that slope, it's going to vary from one point to the next as well along that interval. So what we do is we approximate that slope by finding the slope of the secant line over that closed interval. So when I say secant line, I mean this line right here. A secant line is going to be a line that intersects a curve twice, and I'm going to say locally, which just means in the neighborhood we're looking at. Okay? So if I wanted to find the slope of this green section that I highlighted here, I'm going to find an average slope by finding the slope of the secant line that goes through the endpoints of that interval. So again, if this is the green highlighted interval here, if this is the interval I want to find the slope of, I'm really just going to find an average slope by finding the slope of this secant line. So that secant line would represent the average slope of that green highlighted curve. And we're going to call that an average rate of change because it's approximating the average rate of change of the curve, the rates of change that vary along that section of curve. Okay? So an average rate of change is going to be calculated over a closed interval. So that closed interval, again, just telling us the frame of reference. So from here to here, this is the piece I'm focused on. And over that closed interval, we're going to use a secant line. And a secant line, again, is going to be a line that intersects a curve locally at 2 points. And so what I was trying to explain there, I'm going to say in words here, it sounds kind of fancy, but the slope of that secant line through the endpoints of the curve on that closed interval will represent the average rate of change for the curve on that interval. Okay? So we're going to use some different notation here because it makes sense to do it. If I wanted to approximate the slope of this piece of the curve on this interval that starts here and stops here, I'm going to use this secant line to approximate that slope. Okay? So here's how this looks. Let's say that this point right here has an x value of, let's just call it a. And then this point here, the other endpoint on the interval I'm focused on, has an x value of, let's say, b. Then the y value that corresponds here would be f of a. So this function is called f of x. If I input a into my function, my output, right, is what I would have here for my y. So f of a. And then similarly here, our output we would find by inputting b. So we're going to call this f of b. So the slope of this secant line through those two endpoints is going to be the average slope for this piece of curve that I'm looking at. And how do we find slope? Well, we just said that a second ago. If I subtract my y values, I find my rise. If I subtract my x values, I find my run, and that rise over run is my slope. So in this picture, we're going to say our slope is the second y value, f of b, minus the first y value, f of a, divided by the second x value, b, minus the first x value, a. And that's what we're going to see here as our formula for our average rate of change. It's just slope using a and b as x1 and y1, and f of b and f of a as our y2 and y1. Okay, so it's just slope. Again, we're going to call it an average because it is. It's an average slope for a section of non-linear graph that we're going to be focused on. Okay, so I'm hoping this makes sense. Let's go ahead and try to use this formula to find an average rate of change for a couple of different curves. So for example here, if I want to find the average rate of change over the interval from 0 to 3, this is our frame of reference. I had my highlighter on. So this is our frame of reference. This is telling us the closed interval over which we are to look. So this interval is an interval of x values. So this is our x1 and our y1, or our a and our b, however you want to look at that. So this is saying look from this interval from 0 to 3. So 0 to 3, that's the interval of x values I'm looking at. Okay? So on that interval, my graph starts here and stops here. So if I want to approximate the slope over that interval, I'm going to find the slope of the secant line through those endpoints on that interval. If I was to draw in a secant line here, see if I can do this. Close enough. Okay, the slope of this line is going to represent the average slope for this piece of curve over that interval. So I want to find the slope of that secant line there, that blue line. Well, when we're finding the slope of a line, we're just using y2 minus y1, x2 minus x1, so I need these endpoints. So this endpoint here had an x value of 0, which makes sense, and a y value of -3. And this endpoint here had an x value of 3. Again, this, oh, I put x here. This is not x, this is y. I mean, I put y there, this is x. x2. Man, what did I do? Sorry. So this is 3, and our corresponding y value is 4. Okay, so these are our x values, the starting x value, ending x value, and if we go to our graph, we will find the corresponding y values, and now we have all the information we need in order to calculate our slope. And in fact, if you just wanted to count the rise and the run on that graph, you could, but I'm going to go ahead and use the slope formula. So y2 is 4, minus y1 is a -3, x2 is 3, minus x1 is 0, so we end up here with 4 minus a -3 becomes a 4 plus 3, or 7, and 3 minus 0 is 3, so 7/3. That is the average rate of change over that interval. Now that positive slope makes sense because that is an increasing portion of the graph, and that's something to keep in mind as you're working. If you were finding the slope of a section of graph that was decreasing, then we should have a negative slope. Okay, so if I give you the picture, you're looking for the two end points because you need those 2 points to find your slope. If I give you a function, you could actually make the picture and do the same work, or again, you're asked here to find the average rate of change for this curve over the interval from 3 to 8. They're giving you the x values, where to look. To find the corresponding y values, the outputs, we could just plug those inputs in. And so I'm going to make a little table to organize my work. If I make a table here, I have x values that I'm given, starting at 3, ending at 8. What I want to do is find the function values, the corresponding y values that go with those points. So I'm going to input my 3. If I go to find h of 3, I'm looking at the square root of 3 plus 1, which is the square root of 4, or 2. So there's my output there. And then I'm going to plug in 8, so find h of 8. That would be the square root of 8 plus 1, or the square root of 9, which makes 3. So there's my output there. So in the same way, I'm looking at my graph and trying to find my first location, second location, the endpoints of my closed interval to find my slope. That's what I'm doing here. So they gave me the x's, I found the y's, now I have my two endpoints, and I can calculate that average rate of change, that slope. So in this case, we're going to say our slope is y2 minus y1, so 3 minus 2, divided by x2 minus x1, that's 8 minus 3. And so 3 minus 2 is 1, 8 minus 3 is 5. That means our average slope over this interval is going to be 1/5. And I just want to move this so I can box the whole thing in, and there we have it. Okay, so our average rate of change of that interval is 1/5. Now, positive makes sense to me because I know what this picture looks like. If you didn't, or you wanted to use the picture, remember you could always go to your technology. So if we had the square root of x plus 1 graphically, there's the curve. If we're looking over the interval from 3 to 8, I could also just close this off and say let's only look from 3 less than or equal to x less than or equal to 8. That's the little section we're looking at. I can see it's positive, not very steep, and then I could use those endpoints, and I could see them here at 3, 2, and 8, 3 to find my slope the same way. So you can use your technology to create the picture and use the picture the same way we did number 1, although the algebraic work is not too difficult. Alright, so that's an average rate of change. Now, the average rate of change is going to relate directly to the work that we do in calculus through what we call the difference quotient, along with limits that we saw in our previous topic. So with the difference quotient, we're going to see slope again. So difference quotient is just another form of slope, but it uses some different notation. It's a little more generic than using specific x values like a and b, in that we use a distance from an x value to another x value, and what it allows us to do is actually calculate an equation to find the slope between any 2 points. Okay, so it doesn't matter what interval we're looking at, we come up with an equation that we can use to figure out what our average slope is going to be. So the idea is that it shortcuts the work, but let me show you the notation. Okay. So here's our same situation where if I wanted to find the average rate of change for this curve, I would use the secant line that goes through the endpoints of that curve, and the slope of that line would represent the average slope for this curve. Okay, just same situation, different notation. So what we're going to do here is instead of calling this x value some random x value, we're going to call it x. And that means our first y value that corresponds is going to be f of x. And then the second point here, we are going to say that this point is some distance h. So we're going to call this distance here between these 2 points h, so that this second point is h units away. So that would be the x value we started with plus h here. So h units away. And then the corresponding y value would then be found by inputting x plus h. So this would be f of x plus h here. So now if I wanted to find my slope, it's my second y value minus my first. So f of x plus h minus f of x. And then we're going to divide by our second x value minus our first. So x plus h minus x. Now in our denominator, notice we have a positive x and a negative x, which are going to cancel. That means our slope is going to be f of x plus h minus f of x just divided by h. And that is the formula for what we call the difference quotient. So no matter where we are on a curve, this is going to give us an equation to find our slope if I know where I'm starting and how much further my next point is away from that starting point. So this difference quotient, again, is another form of slope. It's just a little more generic, and it's going to calculate an equation for slope for us. So in this box, we see our difference quotient. Again, still the slope of a secant line of f of x. It goes through our two endpoints here, but instead of calling the x values a and b, they're called x and x plus h. And this is our new formula for slope. It is the same concept, right? It's the rate of change between our points. It's finding an average slope just with some different notation. So let's try to calculate a difference quotient. That means we're going to find an equation for slope for a couple of different functions. So our difference quotient, let me just write my formula up here, says we want to find f of x plus h, and then we want to subtract f of x, and then we want to divide by h. So there's three components here. We have to figure out f of x plus h, we have to subtract f of x, and we have to divide by h. Now, two of those components are simple. So the second one, this f of x, not too bad there. I already know what my function is, so I don't have to do any work for that part. Dividing by h, again, I don't have to do any work there. I'm just going to divide by h. That's not a big deal. This is the place where the mistakes happen. This is where we have to be careful because we actually have to find something when we want to find f of x plus h. So if I said to find f of, let's say, 4, I know that means to input a 4. So if I want to find f of x plus h, that means I have to input an x plus h into my function. So I want to start by finding f of x plus h. So my slope, my difference quotient, is going to be 4 times, in place of x, I'm putting in x plus h, and that's going to be squared. And that's it for f of x plus h. So this is that first component. Now I want to subtract f of x, the function itself. So I want to subtract my 4x squared. So there's my second component. And now the formula says take all that and divide by h. So honestly, half the battle right there, just making sure everything gets plugged in. And now we're going to do a little algebra to try to simplify this. So our slope is going to be 4 times x plus h squared. That's where the real work is going to happen here. That means 4 times x plus h has to be multiplied by itself. And then we're going to subtract that 4x squared. And then again, we're going to divide by h. So we're going to have 4 times, let me do this product here, x times x is going to be an x squared. We're going to get an xh here and another xh here, so we're going to get 2 xh's, and then h times h is going to get us an h squared. Now to that we have to distribute a 4, so we're going to end up with a 4x squared. 4 times 2xh is going to give us an 8xh, and then 4 times h squared is going to give us a 4h squared. So I just distributed 4. So 4x squared, 8xh, and 4h squared, and that's where I got these three pieces. Okay? So from that we said we have to subtract this 4x squared. So a minus 4x squared, and then again divide by h. So we're almost there. We have now m equal to positive 4x squared, negative 4x squared. Those two terms will cancel. So now we're focused on these three terms that actually are, the two on the top are divisible by an h. So now I'm going to divide in h here, divide h here. So if I divide out a factor of h, I'm going to be left with just an 8x plus, again, 4x, or 4h squared divided by h is just going to be a 4h, and that is our equation for our slope, which means no matter what x value we start at and how far away we go from that x value, I can figure out what my average slope is going to be for any curve. So that is an equation that we can use to find the slope of any secant line on any closed interval on any curve. Okay, or in this case, not any curve, but the curve of 4x squared. So no matter what closed interval we're looking at on 4x squared, the graph of 4x squared, this equation could be used to find the slope. Okay, so there's our difference quotient. Let's try with a rational function. Again, I want to find three pieces. Let me move this over so I can reference this. 3 pieces. So first, f of x plus h means x plus h gets input there. So f of x plus h would be 1 over, instead of x plus h. There's our first component. And then I want to subtract f of x. Well, I don't have to find f of x, I have it. So subtract 1 over x. That's my second component. And then my third component is to take this and divide by h. There's my third component. Okay, half the battle. We're good. So now that I have everything plugged in, I want to simplify this. I got to clean this up using a little bit of algebra. Now, I don't know when the last time you worked with a complex fraction was, right? This means you have fractions within a fraction, but I need to actually do the subtraction that's in the numerator here, and to do the subtraction I need a common denominator. So I'm going to multiply this fraction by x over x. I'm going to multiply this fraction by x plus h over x plus h, and now my denominators are the same. They both have a factor of x and x plus h, x and x plus h. So it's like if you're trying to subtract 1/3 from 1/2, right? You'd multiply by 3 over 3 here, multiply by 2 over 2 here. They both have now a factor of 3 and 2, right? So we're just trying to get common denominators to do that subtraction in the numerator. So how does this look now? This fraction becomes x over x times x plus h, minus this fraction becomes x plus h over x and x plus h, right? Well, now that I have those common denominators, I can actually subtract those two fractions. So this becomes x minus h over that common denominator, x and x plus h. And again, this is still all being divided by h. Okay, so we're getting close. Running out of space, which means I'm going to move up here. So m is going to equal, in the top of this fraction, I have an x and a negative x, which is going to cancel. So right now I have a negative h left over x and x plus h over h. Okay, so we're close. Now, we have to kind of read this fraction to understand what to do next. If I have a fraction like a half, and I said divided it by 3, 1/2 divided by 3 is divided by 3 over 1, means we want to take the 1/2 and multiply it by 1/3. So we don't typically divide fractions, we multiply by the reciprocal. Maybe something like keep, change, flip sounds familiar to you. So that's the concept that's happening here. I have a fraction in my numerator, so I have this fraction that I want to divide by h over 1. So let me rewrite this for you. Okay, we're saying negative h over x times x plus h is being divided by h, which is h over 1. So really, I want my negative h and x plus h to be multiplied by 1 over h, in which case we can reduce out that common factor of h. So what we're left with is our difference quotient. The simplified form, it becomes, there's still a negative here, so let's not lose that. A negative times 1 in the numerator, which becomes a negative 1, and then over x times x plus h. So this is an equation that we can use to find the average rate of change over any closed interval on this curve, so long as I know the starting x value and how far away the next x value is. Alright, so that is an equation we can use to find the average rate of change, any secant line on this curve. Now obviously that one was a little more work. Fractions tend to make that the case, and I showed probably more work than I would have on my own, and if you're comfortable with fractions and you're recently coming out of college algebra, then maybe you can shortcut some of that process too, but hopefully I didn't lose anyone in there. But there you have it. Okay, so that's our difference quotient. Now what I want to show you next is the limit of the difference quotient as h, the distance between our 2 points, approaches 0. This is going to allow us to calculate what we call an instantaneous rate of change. So we're going to consider the limit of the difference quotient as h, that's the distance between the 2 points we're looking at in that closed interval, as that distance approaches 0, or as that distance gets closer and closer, or gets smaller and smaller, so the distance between the 2 points becomes 0. Okay, so same situation again. We're starting at some x value, and we're ending at that x value but h units away. So some distance h, this distance in here, is going to be h. What's going to happen as the distance between those 2 points gets closer and closer together, or as the 2 points get closer and closer together, as the distance between them gets smaller and smaller and smaller. So if I was to, instead of taking these 2 points here, if I was to make the distance shorter, so make h a little bit smaller, so let's close the gap there a little bit, then we'd have a new secant line, right? And we have a slope that better approximates the average rate of change of this piece of the curve. Or if I made those 2 points even closer together, so let's say I put the 2 points here, made distance between them smaller, again we'd have this new secant line here. Well, as h approaches 0, as the distance between those 2 points gets smaller and smaller and smaller, infinitely small, what happens is, instead of having a closed interval, those 2 points converge to a single point, and instead of having a secant line, we have a, that was a terrible line, we have a tangent line. So if we get the distance between those 2 points to become, there, that looks pretty good, become infinitely small as h, the distance between those 2 points, gets closer and closer to 0, what we have is our closed interval converging to a single point here. And so now we can find the slope of that tangent line. That's a line that intersects the curve locally just once, and that slope of that tangent line represents the slope at that one point, that one instant on the graph. And so the slope of that tangent line is going to represent what we call the instantaneous rate of change. It's the slope at a single point instead of the slope over an interval. So as h approaches 0, that closed interval, the interval between the 2 points, converges to a single point. And we're going to say that the slope of the line tangent to our curve at that point is the instantaneous rate of change for the curve at that point. And again, the tangent line, that's the one in pink there, is a line that intersects the curve locally at one point. And again, I use this word locally because we just want to look in this neighborhood. It's possible that somewhere farther out the tangent line intersects the curve again, but we're not concerned with that. We're just concerned with this neighborhood, this local area. Okay, so that's what I mean to say there. And so here we have it. A definition now for an instantaneous rate of change. So if I want to find an instantaneous rate of change, I'm looking for a rate of change at a point, which means the distance between 2 points in a closed interval is going to get smaller and smaller and smaller. So we're going to do this by using our difference quotient. That's what I see here, right? This is our difference quotient. But let's find the limit as h, the distance between those 2 points, approaches 0. And we do that by actually plugging 0 in for h. So we're going to find our difference quotient, and then we're going to evaluate it at h, and that's going to give us the instantaneous slope for our curve at a specific point. Okay, so we're going to find our difference quotient, we're going to evaluate the limit at 0, and that's going to give us our slope. So let's try it. If I'm looking at x squared plus 5 as our function, and I want to find the instantaneous rate of change, I want to first find the difference quotient, and then approximate that the limit of that difference quotient as, in this case, x approaches 2. Okay, so let me write out what I have to do here. I need to find the limit of x squared plus 5 as, not just this, kidding. Just kidding. I want to find the limit of the difference quotient for x squared plus 5. So when I find the difference quotient, remember that's 3 components. That's f of x plus h. So this is going to be, instead of x squared plus 5, it will be x plus h squared plus 5. Okay, I don't want to lose anyone. So difference quotient first, okay? So f of x plus h in the top, and again, this is going to be a slope. So we want, let me go back. F of x plus h will be x plus h squared plus 5. So same function, just replacing x with x plus h. That would be like the first component. Was I using yellow before? Sorry for the scrolling if that's losing you. So this piece, that's what I'm doing here. Okay, there's my x plus h, f of x plus h. And then I want to subtract. The second component is f of x. So I want to actually subtract this entire function. Now the first two examples we did with the difference quotient only had a single term. We have to be careful here. I want to make sure I subtract the x squared and the positive 5. So the whole function has to be subtracted. So there's my f of x, my second component. And now I need to divide that by h. So we'll take this and divide by h. There's my third component. Right, so that would just be the difference quotient, and that would get us an equation for the average rate of change. Now, what I'm saying is, if I want to find the instantaneous rate of change, I find the limit of that difference quotient as h approaches 0. All right, so there's that extra component. So let's go ahead and work on the difference quotient first. And I'm going to change colors here, so I'm going to do a little bit of side work. I want to clean this up the same way I was cleaning up the difference quotient before. So I need x plus h squared, which means that's got to be multiplied by itself, plus a 5 minus, distribute the negative here, and x squared and a negative 5, and that's all going to be divided by h. So that's going to become, excuse me, an x squared, an xh here, another xh here, so two xh's, and then an h squared. And then I have this positive 5 and negative 5 that are going to cancel. And then I have a minus x squared. Well, let me just bring it all down. A plus 5, a minus x squared, a minus 5. And again, this is all divided by nh. So I have some things canceling. I have an x squared and a negative x squared. I have a positive 5 and a negative 5. So now I'm left with, I'm so sorry, this little piece to simplify. And the two terms in the numerator have an h that I can actually divide out. I'm going to divide by h. So what I'm left with is a 2x and a plus h. So divide the h in here, divide the h in here, and this is my difference quotient, okay? So now what I'm trying to do, again, is find the limit of my difference quotient, which I just said is now 2x plus h, as h approaches 0. Well, we know how to find a limit. All we need to do is input this value, if that's a possibility, and it is here. There's nothing that's going to cause a restriction. So now I find this limit by actually inputting, I need a different color here, 0 in for h. So this is going to be equal to 2x plus 0, which is just going to be 2x. So here we have an equation for our slope over any interval, right? This would be our equation for our slope. But we're not looking at any particular interval. Remember, we're looking at the slope for a particular point, and it tells us here that point. It says, let's look specifically at x equals 2. So we got an equation for our slope, right? We said our slope is going to be equal to 2 times x. Well, now let's just input that value of x. So in this case, our slope is going to be 2 times the x value of 2, which makes it 4. So our instantaneous rate of change on this curve at that location is 4. Okay, so let me try to show you a picture of what this means, and this is going to be the answer here. Okay, that's the answer. Now that I've circled and highlighted and boxed, I don't know if that's clear, but hopefully it is. So the slope, the instantaneous rate of change for this function at that x value is going to be 4. So let's just look at the graph so you can try to wrap your brain around what all we just did. So x squared plus 5, here's our parabola. What we're saying is if we focus on this x value of 2, so an x value of 2 to, 9 is where we're looking. Okay, that's the point we're looking at there. At that point, if I was to draw a tangent line, the tangent line at that point would have a slope of 4. So we have this parabola at x equals 2. If I drew a tangent line, the slope of that tangent line is 4. That's what we're saying. Okay? Hopefully that makes a little bit of sense. But it's difference quotient, and then the limit of that difference quotient as h approaches 0. That gives us an equation for our slope. We plug in the x value we're looking at, and then we're done. Okay? Now let me see if I can highlight. I'm going to get rid of this circle. And just try to highlight, so later on when you come back to this, you're like, what did she do again? Once I have this, I have to plug in my x value, and then I'm done. Okay? So difference quotient, the limit as h approaches 0, and then input the given x value. So let's try it once more with a rational function, which is going to easily become your favorite thing to do. So I'm finding the slope, the instantaneous rate of change, by finding the limit as h approaches 0 of the difference quotient. So the difference quotient is going to be f of x plus h. So I need to plug in an x plus h there. So it's going to be 2 over x plus h minus 4. And then from that I want to subtract f of x, which is the function itself, so 2 over x minus 4. And then from that I want to divide by h. So there's my difference quotient. So find the limit of that difference quotient as h approaches 0. Now I'm going to do some side work to clean up this difference quotient before I actually try to find the limit. So these two fractions need to be subtracted. I need a common denominator to make that happen. So I have 2 over x plus h minus 4. I'm trying to subtract 2 over x minus 4, and then I'm trying to divide by h. So I'm going to multiply this fraction, and I'm pretty sure I said change to green. And actually, maybe not green. It's going to run into my other work. Let me use pink. This one by this denominator, so x minus 4. And this one by the other denominator, x plus h minus 4. And now my denominators look the same. They both have a factor of x minus 4. They both have a factor of x plus h minus 4. So this becomes, if we look here, this becomes 2x minus 8 in my numerator. And then this, I'm going to put this negative here, becomes negative 2x minus 2h, negative 2x minus 2h, and then plus 8 in that second numerator, and that's going to be over my common denominator, which is an x minus 4 and an x plus h minus 4. Okay, and that is all still being divided by h. Now some cleanup. 2x and negative 2x will cancel. 8 and negative 8 will cancel. So I'm left with a negative 2h over the common denominator, x minus h, x, oh not h, 4, x plus h minus 4. Now if that's being divided by h over 1, then we can multiply by 1 over h, and then again reduce. We got a common factor of h, that goes away, and so our difference quotient ends up being a negative 2 over x minus 4 and x plus h minus 4. So that's our difference quotient, okay? So now let me go back to this, and I probably should have written smaller, sorry. This means now I want to find the limit of my new function. My difference quotient is going to be negative 2 over x minus 4, x plus h minus 4. This, oh, I'm out of space. There we go. Find this limit as h approaches 0. Now you might be wondering, why did we do all that work of simplifying the difference quotient? Remember, the goal is to try to take this 0 and plug it in, and I can't do that with that h in the bottom. So the work of simplifying was necessary so that now I can actually input the 0. So now I want to actually find the limit as h approaches 0 by inputting the 0. So 0 is going to get plugged in where I have an h, which is going to be right here. And so this slope becomes -2 over, I'm going to have an x minus 4, and then x plus 0 minus 4 leaves me another x minus 4. So that's the equation for my slope. Okay, that's the equation for my instantaneous rate of change. Now, if I didn't have an x value, I would just leave it here, but it's saying, let's find it at x equals 1. That means plug 1 into x now to actually find the slope at this point. So now I'm going to say my slope is -2 over, if I plug a 1 in, 1 minus 4 and 1 minus 4, we're looking at -2 over -3 times -3. So that makes a final -2 over 9. That is going to be the slope, the instantaneous rate of change of that function at that point. All right, so that's a lot of slop there. I'm sorry my work got a little bit messy, but hopefully you're following. It's the work with the fractions there, the actual college algebra, that's hard. I don't think the calculus part of this is that difficult. But again, let me show you graphically what we're saying here. So if we look at the graph of 2 over x minus 4, and focus on the x value of 1. So at an x value of 1, where are we? So 1, and this would be, if I plugged a 1 into my function, I would have 2 over -3. Okay, that's the point we're focused on. So what we're saying is, if we had this graph, and we drew in a tangent line at that point, the slope of the tangent line would be -2/9. Okay, so if I put in a tangent line at that point, let me try to, here's the little branch we're looking at, here's the point we're focused on. If we put a tangent line to that point, the slope of that tangent line, the instantaneous rate of change, would be -2/9. Okay, that's what we've found in this problem. And you're like, why? Why are we doing this? Well, it's calculus in a nutshell. Calculus in a nutshell, Calc 1 at least, is finding instantaneous rates of change. And this is the long way to do it. There are going to be much faster ways to find these things moving forward, but this is sort of the definition of what we're going to get to in our next topic, which we call a derivative. All right, so something to look forward to, and they won't all be this complicated, I promise. But for now, you're finding slope, okay? That is the concept that you need to hold down. It's finding slope, that's just different notation and different ways to find it depending on what kind of curve we're looking at. So I think you've got enough to get going on your assignment, but as always, if you have questions, you need help, then just reach out. Until next time, take care.